Welcome to lecture number 5 in Multiple Antenna Communications at Linköping University. In this lecture, I will first wrap up the topic about point-to-point MIMO and talk about some of the practical issues with achieving the gains that we have been deriving in the previous lectures. Then I will provide an introduction to an alternative type of MIMO called multiuser MIMO. I will talk about the uplink and downlink. And then we will talk about orthogonal access versus spatial multiplexing. And finally, I will spend some time talking about the capacity region, different operating points, and drive the uplink capacity in some simple setups. So let's first talk about the point-to-point MIMO capacity again. So what we have been saying in the previous lecture is that we should analyze such a channel by computing singular value decomposition of the channel matrix. So we have the channel matrix G, which is an M by K matrix. M is number of receive antennas and K is number of transmit antennas. And we can divide this channel matrix into 3 different parts. The left matrix here is U. That one is called the left singular vectors, and it contains U1 to UM. These are the columns. And the receiver is utilizing this matrix in order to separate the received signals into different dimensions. And then we have V, which is also a unitary matrix. It contains the columns V1 to VK, and the transmitter should utilize this matrix, these columns, in order to send the signals in different orthogonal directions that are matched to the channel. And in that way, we can divide the point-to-point MIMO channel into capital S different parallel channels, and each of them have a gain, S1 to S capital S. And these are appearing in this matrix sigma, which is a diagonal matrix or rectangular matrix with these values on the main diagonal. Using this notation, we can also write the channel matrix G as a summation over the capital S different singular values that are non-zero, all of them. And then for each one, we have the singular value. We have one of the columns in U and one of the columns in V. And this is how we are decomposing our channel into S parallel channels, each being represented by one of the different terms in the summation here. So one way of viewing the channel matrix is that from the transmitter to the receiver, we have this channel, and it contains different V vectors here, V1, V2, V3, that are representing different orthogonal ways of the signals propagating from the transmitter. Then we have the U vectors, U1, U2, U3, which are representing different orthogonal ways that the signal can reach the receiver. In each of these combinations, U1, V1 is representing one way that the signal can propagate from the transmitter to the receiver, and the corresponding singular value saying how strong that type of path is going to be. And in some cases, we can view this geometrically as, okay, the first path here is representing a direct path from the transmitter to the receiver. The second path, the red one here, is describing one way that the signal is propagating from the transmitter via a scattering object and then reaches the receiver. And the green path here is another scattering object that is also spread out. So in some cases, a MIMO channel can be viewed geometrical like this. We have different paths, they are representing different objects that the signals are bouncing off. But in practice, this only happens in extreme cases when you have few propagation paths compared to a number of antennas, so that you can really separate the channels in different ways. Usually, we should just view this U1 and V1 as being different ways that the signals can be reaching the transmitter and receiver without mapping them to particular scattering objects or something like that. It is, of course, important to keep this in mind as one way of interpreting the channel, but also to remember that in most cases it doesn't work like that. It's more complicated. What are then the problems with point-to-point MIMO that I was mentioning earlier? Well, the main benefit of point-to-point MIMO is that if S is the rank of the channel matrix, then we can spatially multiplex S signals at the same time. And at highest now, that gives us a roughly S times larger capacity than in the sizer case. But in the line of sight cases, we saw in the last lecture that the channel have a rank that is equal to 1. And even if you add a few additional scattered paths, they will be much weaker than the direct path, and therefore you still have approximately a rank 1 matrix. In non-line of sight cases, for example with IID rayleigh fading, you will see that the rank has its maximum value, which is the minimum of M and K. But the problem is that in non-line of sight channels you seldom have a high SNR scenario. So I would say that the main benefit of point-to-point MIMO in practice usually is the beamforming gain. Because when you have a high SNR, so you can benefit from multiplexing gain, then you are likely to be in a line of sight case where the rank is low. And when you have a low SNR, well, then you're likely to have a high rank because you are in non-line of sight scenarios, but then you don't benefit much from a multiplexing gain. We saw that at low SNR, it is the beamforming gain that is the important thing, because you only want to allocate power to one or a few of the strongest of the single values. So this is also represented in this graph here. We see the capacity versus the signal to noise ratio, and the dotted line down here, this is the SISO capacity. Then we have the solid black line. This is non-line of sight, and we see that we are getting a much faster scaling here with the SNR at high SNR. And in this case we have 4 antennas, so we have a 4 times higher slope. But in many non-line of sight scenarios we have low SNR, and then we are down here where the gap from the SISO curve is not so large as compared to the gap at higher SNRs. In the line of sight cases it's more likely that we have a high SNR, but we don't have a multiplexing gain. So even if we get the beamforming gain, which is moving the curve to the left here, we don't have a big gap to the SISO case here as well. There's also other practical problems with point-to-point MIMO, and that is that the multiplexing gain is given by the minimum the number of transmit and receive antennas. So we need to have multiple antennas both at the transmitter and at the receiver. And one of these devices is probably going to be a user device, maybe a handheld mobile phone or something like that, and we can't fit many antennas into such a device. That also limits the ability to use point-to-point MIMO in practice. An option in order to improve the situation is to consider multi-user MIMO instead. So in this case, we have multiple antennas at a base station, but instead of having multiple antennas in each device, we have multiple devices instead. And we have 2 scenarios, the uplink and the downlink. In the uplink, the users are transmitting to the base station, so this is a multiple point-to-point MIMO setup. The multiple points are the users, and the 1 point here is the receiving base station. Then we have the downlink, and this is going from the base station to the users. So this is a point-to multipoint MIMO setup. So we have multiple antennas at the transmitter, and we have multiple receiving users. And we are indicating here that we are sending different beams to different users at the same time and frequency, while here we are having different users at different locations transmitting signals at the same time. And the reason that we call this MIMO, even if we only have 1 antenna in each user device, is because we have multiple points where the antennas are located. So it's a multi-point-to-point MIMO or point-to-multipoint MIMO case. And let us first look at a basic case of how a multi-point-to-point setup can work. And let's focus on the uplink, and the basic or classical scenario there is what we call orthogonal multiple access. So we have 2 users, user 1 and user 2, who would like to transmit to this base station here. And both of them have a power that we are calling P, and this is in watt. They have a bandwidth that they need to share that's called B, and we have a noise power spectral density N0. And for simplicity, we assume that both of them have a channel gain of beta, so they have the same channel quality. In orthogonal multiple access, the users need to share the bandwidth in an orthogonal manner, which means that we are dividing the bandwidth between the users. So let's say that we are having alpha as a parameter, and then user 1 is getting alpha times b as its fraction of the bandwidth. And then the remaining bandwidth, 1 minus alpha times b, is assigned to user 2. Then we can compute 2 achievable rates of these 2 users. The first user is having the bandwidth alpha times b, so we put this in front of the logarithm. We have log 2 of 1 plus a signal to noise ratio, which contains the total power p, beta, which was the channel gain, and then we have the bandwidth alpha times b again, and we have n naught as the power spectral density of the noise. For user 2, we are instead having another bandwidth, 1 minus alpha times b. We have log 2 of 1 plus the same power, the same channel gain, the same noise power spectral density, but a different bandwidth. And now, for a given value of alpha, we can achieve a certain pair of rates here, R1 and R2. And we can also vary alpha to achieve different pairs. So remember, here were the different rates that we can achieve. And let's say that these are measured in bits per second, but we can divide with the bandwidth to get the bit per symbol. And here is then the result. We assume that P times beta divided by B times N naught is equal to 10 decibel. So that is an SNR that you achieve if you are assigned all the bandwidth. Then here we are showing the rate that user 1 is getting and the rate that user 2 is getting measured in bit per symbol. If we select alpha equal to 0, then we put no bandwidth to user 1 and all the bandwidth to user 2. In that case, it gets its maximum rate. It's up here. If we are instead selecting alpha equal to 1, we give all the bandwidth to user 1 and no bandwidth to user 2. Then we are down at this point here, where we have the maximum value for user 1, but no value at all for user 2. And if we are sharing the bandwidth equally between the two users, alpha is equal to 1/2, and we will get the point here where both of the users are getting a value. So R1 and R2 are non-zero, both of them. And by varying alpha from 0 to 1, we move along this curve here and can achieve different trade-offs in terms of the performance that we can deliver to these different users. So what is the preferred operating point here? We can achieve all the points on this black curve here, but which one should we choose? Well, we will come back to that, but we will first look at another option of doing multiple access. This was orthogonal, where we are dividing the bandwidth between the users orthogonally, but we can also do a non-orthogonal option. So in this case, we let both of the users transmit simultaneously on the same bandwidth, which means that the received signal, Y, we still only have one antenna at transmitter and one at the receiver, then this received signal Y is equal to X1, which is the signal coming from user 1. We assume that the user is using a complex Gaussian signal with power P, so it's still the same maximum power. Then user 2 is sending the signal X2 at the same time, and it's also being Gaussian distributed and have a power of P. And N is noise, it has a power that is B times N naught. So how can we deal with the signal like this? What can the receiving base station do? Well, here's the strategy. It can focus first on user 1, and then X1 is the signal of interest, and then X2 and N are interference and noise. And both of them are going to be Gaussian distributed, both the noise, which is natural like that, but also the interference, because that is the type of transmissions that we selected. And then if we treat both of them as being Gaussian noise, which they essentially are, then we can compute a rate, log 2 of 1 plus a signal to interference and noise ratio. We have the signal power P here from X1, we have the power P from the interfering signal, plus the power of the noise, B times N naught. So this is a rate that user 1 can get if the base station is decoding the signal like this. Then, after the base station had decoded this signal, it knows what X1 is. So therefore, it can subtract X1 from the received signal Y. And what's left then is X2 plus N. So this is just signal in noise. And then we can decode this signal from user 2 without an interference. So R2 is log 2 of 1 plus the SNR, power P divided by the noise power. So this is one strategy that we can apply. This is called successive interference cancellation, because we are first decoding one signal and then we are subtracting that signal, and then we're decoding the next one in a successive manner. And if we have more than 2 users, we can continue like this. And we can also change the user ordering. So we can first decode the signal of user 2, and then we will get a similar rate for that user. And then we can decode the signal of user 1, then this user will get this rate, You just need to change R1 to R2 and R2 to R1, and then we can get the same result. So what are then the benefits of using non-orthogonal multiple access? Well, we can actually improve the rates of both the uses in many cases. So the black curve here is what we achieved before with the orthogonal axis. So we still have user 1's performance here on the horizontal axis and user 2's performance on the vertical axis. And the blue curve is what we can achieve with non-orthogonal axis. So how is that possible? Well, here is one point down here where we are only serving user 1. So in that case, we have an orthogonal axis. We give all the performance to that user. Then we have another single user point where we are assigning all the resources to user 2 and it's not serving user 1 at all. Then we have the option that I was describing where we are first decoding the signal for user 1 and it is then getting this rate here, which is this point. And then user 2 can actually get exactly the same rate as if it were alone in the system. So of course we shouldn't use 0.2, we should use 0.3 instead. And then we have a fourth point, which is down here. That's when we are switching the order. So now we are decoding first for user 2 and get this rate here, which is lower and which involves interference from user 1. And then after we have decoded that signal, we can subtract interference and user 1 will then get the same rate as if it was alone in the system. So of course we should use 0.4 instead of 0.1. Then we can do something called time sharing, which means that, okay, we have these 2 points, 3 and 4, which are making good sense. But if we're not satisfied with any of those points, we can pick any point in between them by just saying that we are going to operate at 0.3 part of the time and at 0.4 part of the time. In that way we get a combination of them. By changing the fraction of time that we're using 4 or 3, we can move along this line. So if we start with only using 3, we are here. Then if we are using part of the time for 0.4 instead, we are moving towards 0.4 along this blue line here, and eventually we are reaching it. And we can see that at the point where we are giving equal time to 3 and 4, we also get exactly the same rates for the two uses as in the orthogonal multiple access case when they were giving half of the bandwidth each. But in general, we get a larger region here. And actually, this is called the capacity region of something like this, because this happened to be the best way of operating. So that is the motivation to serve multiple users at the same time in the uplink. And it will actually be much easier to do that when we also have multiple antennas at the base station. That is something we will be motivating more in this lecture. So let us just introduce some basic notations. We have K single antenna users that are transmitting in the uplink. So from user 1 to user K. And these users can be distributed in any way we like. And then they are sending different signals to the base station, which is having M base station antennas. And we'll let the channel response from user I to antenna J at the base station be denoted as GJI. So the superscript J is describing which base station antenna is receiving the signal, and the subscript I here is describing which user is transmitting. The signals transmitted by the K users are called X1 to XK, and the received signals at the base station are Y1 to YM. So we see that the signal from user 1 is reaching all of the receive antennas. The signals from user I is also received to all the antennas, and so on. So we get a mix of signals from multiple users at the receiver here, and its task will be to separate them. And that would be particularly easy to do when we have at least as many base station antennas as we have users. So we can write all of these signals in a matrix form, where Y here is a vector containing the received signal at the M antennas, Y1 to YM. Then we are having X, which is the transmitted signals from all the users, X1 to XK. We have W, which is the noise, W1 to WM. So this is the noise observed at each of the M receive antennas. Then we have a channel matrix where we are gathering all of these channel responses between the different users and the different receive antennas. So we see that we have G11, G1M, GK1, and GKM, for example. So all of them are in this matrix. And from now on, we will also start normalizing our parameters much more than we've done earlier, because I think now we know how to deal with those type of things. So we will say that we have row uplink, or UL. This is describing some kind of normalized signal-to-noise ratio, and it's appearing here. And then each user has a signal power that is limited, but we have normalized it such that the expected value, or the absolute value squared of the signal for user K, should be small or equal to 1, and not some particular power P, because all of those things are in this row term instead. And also the noise variance have been normalized, so we are moving it into row uplink here as well. So therefore each of these elements in the noise vector having a variance 1. And we can always do this without loss of generality. We can take y and divide by this true standard deviation of the noise, and that way we can move it from W to row uplink. And since we have a product to row uplink and x here, we can move its power to row uplink as well without loss of generality. So this is the basic description of the uplink in multiuser MIMO. And you might recognize it because it looks very similar to the point-to-point MIMO case, where we also are receiving a m-dimensional vector, we are transmitting a k-dimensional vector, we have a channel matrix G. The elements here are on purpose denoted in a different way, but the matrix itself is still an m by k matrix. And we have a noise vector that we also purposely are denoting with W now instead of n, but it's still an m-dimensional vector. So it's the same kind of principles here. So what is the difference then from a point-to-point MIMO case? There are actually 4 very important differences that will make the analysis rather different. The first one is that the users do not cooperate. So x1 to xk are going to be independent data signals. And this is very different from the point-to-point MIMO case, where the optimal vector x was created by taking an information signal and multiplied with the matrix coming from the singular value decomposition of the channel. And in that way we will take the information and we'll spread it out over the antennas in different ways. But here we want to have independent signals because the users have their own signals to transmit. The second difference is that each user cares about its own performance. So there is not one performance metric that is describing the whole system. Instead, when we have k users, we need to care about k user capacities instead of just one capacity. So even if we were spatially multiplexing capital S different signals in the point-to-point MIMO case, we only cared about the sum of the rates over these parallel channels. But here we have k users that are interested in their specific rates or capacities. Difference 3 is that each user has its own power budget. So for each of these signals, we take the absolute value square, we compute the expected value of it, and that one should be small or equal to a number. And that is also different from the point-to-point MIMO case, where we could spread out the signals over our different parallel subchannels, and we have the total power over those subchannels that we cared about, and that's why we derived the water filling algorithm, for example. And that is not used here because every user have its own power amplifier, and its own battery that is drained by using the power. Difference number 4 is that the channel matrix G is modeled very differently from the point-to-point MIMO case, even if the equation y is equal to G times x plus n is very similar. And in particular, each column of G is now describing a SIMO channel from one user to a base station with multiple antennas. And that column can be modeled in similar ways as we have been talking about before, but the different columns are modeled differently because the users are at different locations, have different propagation conditions. And that gives us a bigger chance that the channel matrix G have good properties, such as a high rank, and that is giving us the possibility of communicating with more data over this type of multi-user MIMO channels than in the corresponding point-to-point MIMO channel. The rest of this course is going to focus on multi-user MIMO, so let me explain you the motivation behind this. So I started today with talking about orthogonal access with one receive antenna. So then you had 2 users and they were splitting the bandwidth between them. And then we were getting this curve here that is describing which are the pairs of rates that the two users can get at the same time. Then I mentioned the non-orthogonal access, still with one antenna at the receiver, and we can expand the region in this way. For example, one user can get its maximum rate while the other user is getting a non-zero rate, and that is achieved using successive interference cancellation. And multiuser MIMO is essentially a non-orthogonal access scheme, but we are usually not calling it that, but multiuser MIMO. And the benefits it has is that the region is going to be much larger here. So there are two benefits. The beamforming gain that we achieve by having multiple receive antennas is increasing the rate that each user can get when it is alone in the system. And also, by having multiple antennas, the different rows in the channel matrix are going to look more and more orthogonal to each other, which means that the user are interfering less and less. And that will also mean that this trade-off here between them is going to be smaller. So if we would like to serve one user with its maximum rate, the loss for the other user compared to its maximum rate is going to be smaller than in this non-orthogonal access case. And that can also give us the opportunity to use simpler methods for receiving the signals than successive interference cancellation. So in some cases we are talking about a rate region, and in some cases we are talking about capacity regions. And it's often safe to say rate region because that is describing achievable rates that different users can get at different points. So all the points in a region like this are achievable in one way or another. The capacity region is the largest possible rate region, and then we need to make sure that we are operating our system in the optimal way. The capacity region is guaranteed to have a particular shape because we can pick 2 points in the region and we can use them a fraction of the time. This is what I called time sharing earlier, and in that way we can achieve any other operating point in between those 2 points. And as a conclusion, that means that if you take any 2 points in the region and draw a line between them, then all the points there on that line must also be inside the capacity region. And the conclusion is that the region must be a so-called convex set. So here is a possible shape of a capacity region where we have these blue points here that we can choose between, and if you take 2 points and draw a line between them, well, then we are still inside the region. Here is an alternative shape that is not possible for the capacity region, because if we take this point here and that point here and we draw a line between them, then we will get operating points that are outside the region. So this is not a capacity region, while this can be a capacity region. And the boundary here is called the Pareto boundary. So the capacity region is containing a lot of different points. So here in this two-dimensional case, we have 2 users. R1 and R2 are the rates that they can achieve, and inside the region here we achieve some points, and then on the boundary we achieve other points. And the true capacity is always lying on the boundary here. So even if we have a lot of different choices to make between which operating point we would like to have, we should always pick something on this outer boundary, which we are calling the Pareto boundary. And the reason for that is that if we pick a point in the middle of the region, this one for example, then we can improve the performance for user 1 and for user 2 and still be inside the region. So that was not a good starting point. But if we are picking something on the boundary, the only way to improve the performance for user 1 is to move to the right here, and then to stay inside the region we need to reduce the rate for user 2. And then we have a strict trade-off, and we need to figure out which point on this boundary to pick. And there are many choices here, and there is no optimal one. So for example, maybe you're caring only about the performance for user 1, well then you pick this point. And if you're only caring about the performance for user 2, you pick this point. Another option is to say that I would like to send as much data as possible through my system. Well then the sum of the rate of user 1 and the rate of user 2 is the preferred choice, and then we will end up in this case at this point. And then if we are instead caring about some kind of fairness between the users, then we will like R1 and R2 to be equal, and in that case we pick this point. And why do we want to enforce this type of fairness? Well, if we are just caring about the sum of the two rates, then it might be that one user doesn't get any rate at all. And this is similar to the water filling that we talked about in the previous video, where we saw that we could have multiple sub-channels, but we only allocate power and use some of them. And in the same way, if we are maximizing the sum rate here, it might happen that we are not giving any power to one of the users, and therefore it gets zero rate. There is some kind of fairness scale between the maximum sum rate, which cares only about sending as much data as possible without caring about who is the transmitter of that data. And the maximum fairness case where everyone is getting the same rate. And by doing so, it doesn't help if you are having a better channel or not, because you will always get the same rate as everyone else. And you can make a case for that your system that you are building is going to be anywhere along this scale here, and there is no right or wrong answer here. As long as you pick a point on the Pareto boundary, then you have an optimal solution in one sense. So let me just wrap up with talking about the sum capacity of an uplink multiuser MIMO channel. So recall that we had this received signal, Y, which is the channel matrix G multiplied with the transmitter signal X, and then we have the SNR here and we have the noise vector. Then assume that the channel G is deterministic and fixed, so we have a non-fading channel. And let's assume that all users are transmitting with full power. This means that the vector X is going to be complex Gaussian, and its covariance matrix is an identity matrix because all the elements in X are independent of each other and have variance 1. That was the maximum power when we have normalized our system, so rho uplink is the total power. Then this is very much like a point-to-point MIMO channel, but with a suboptimal way of selecting the transmission. So we have a signal covariance matrix for X here, which is an identity matrix, which was not the optimal choice. We wanted to select it based on the single value composition of the channel. But in the multi-user MIMO system, we cannot do that because the users are not cooperating. So therefore, it turns out that this is actually the optimal strategy if we would like to maximize the sum capacity. And one can show that the sum rate of a point-to-point MIMO channel when using this signal covariance matrix is like this. We sum up the rates of different users, and then we get the log2 of the determinant of an identity matrix, which is the one in the log expression, plus the SNR. And then we have the G times G Hermitian term. So this is the channel matrix that is appearing here. And this is actually the sum rate for a point-to-point MIMO channel, but the sum capacity of an uplink multi-user MIMO system. And we achieve it in the same way as we have exemplified earlier, successive interference cancellation. The derivation is just a bit more complicated because now we have vectors and matrices that we need to play around with in order to find the best way of decoding different signals. But the principle is that we decode the signal from one user first, while treating the interfering signals from the other users as being part of the noise, and then we have some colored noise to deal with. Then, when we have decoded that signal, we subtract the interference from Y, and we are decoding for another user, while treating the remaining interfering signals as being part of the noise. And then we do this successively until we only have one user left. That user is now having an interference-free channel, and that user will then get the full rate that it would be able to get without any interference at all in the system. And the sum rate here is always the same, irrespective of the decoding order of the users. But by deciding who's decoding when, we can determine how we should take this rate or capacity and divide it between the different users. And that way we can create different operating points. And the users that are decoding late are the ones who are getting the least effective interference, so they get a larger share of the sum capacity. Here is an example of the entire uplink capacity region when we have two users. So the capacity region is describing all the rates R1 and R2 that we can achieve simultaneously for these two users. And we let the channel matrix be divided into two columns, G1 and G2. G1 is the channel from user 1 to the base station, and G2 is the channel from user 2 to the base station. And if we are serving only one of the users, then if we serve user 1, we have a SIMO channel. We know the capacity is log2 or 1 plus the SNR, and then we have the squared norm of the channel vector. And if we are serving user 2, then we have a capacity of log 2 or 1 plus row uplink times the squared norm of its channel vector. And then from the previous slide, we saw that the sum capacity, R1 plus R2, is log 2 of the determinant of an identity matrix plus row uplink. Then we multiply the channel matrix with its conjugate transpose. And now we have some different operating points. At this point, we are only serving user 1. At this point, we're only serving user 2. Then we have the opportunity of applying a successive interference cancellation to achieve this sum capacity. And we do it by first decoding the signal of user 1. And then we can decode the signal of user 2 and achieve its full capacity. So then we get to this point. Then we have the other option of being here, when we are first decoding the signal of user 2, so it gets a lower rate, and then we have no interference left, so we can decode the signal of user 1 without interference, so it gets its full capacity. And if we do time share, we can select points in between 3 and 4 here, and the same way we can achieve points along these lines as well. So this is the uplink capacity region with 2 users, and it is determined by 3 equations. The first equation here is saying that the achievable rate should be smaller than the capacity of the first user. That means that we should be on the left side of this vertical line here. The second equation is saying that the rate of user 2 should be smaller or equal than its capacity. So that means that we should be along this line or below it. And then R1 plus R2 being smaller than the sum capacity here is saying that this is like a line equation that is representing this line here, and that we should be below that line, so to the left of it. So in summary, we wrapped up the point-to-point MIMO channel case by saying that the large multiplexing gains that these type of methods can deliver might be hard to achieve in practice. And that motivates why multi-user MIMO channels are of particular interest in the future. And we have a similar system model, but some very key differences that makes the analysis different. We have independent users that are sending independent signals in the uplink, and in the downlink they're also interested in different signals. They are using different power sources, so therefore they need to have different power constraints, and they have different performance metrics. So we have one performance metric per user instead of one in total for the entire system. That means that when we talk about capacity and rates, well, then we need to draw regions that are having a dimension that is as large as the number of users that we're having. And in this video, I only showed you 2-dimensional examples, but one can extend this to more dimensions. And I was also talking about orthogonal and non-orthogonal access. And multi-user MIMO is a type of non-orthogonal access where you let all the users transmit at the same time and you get interference between them, but you deal with that using multiple antennas. But usually we are not calling it non-orthogonal access, but multi-user MIMO. So this is the end of lecture 5 in multiple antenna communications.